we've got quite a sizable chunk of lithium, I think. Alrighty, in the recent past you may have noticed that on Scrap Science we've been dedicating a few videos to extracting metals that require the electrolysis of molten salts. So far we've extracted aluminium metal and we've extracted sodium metal. This type of metal extraction by the electrolysis of molten salts is eventually going to become a kind of series on the channel. I've got a lot planned for it, and we've started out with some of the simple ones to try first, that being aluminium and sodium, and we'll be moving up in difficulty as time goes on. Anyway, having finished the isolation of aluminium and sodium, we've kind of finished with the easy molten salt electrolysis projects. I say easy because these processes that we've completed so far haven't generated any toxic gases, haven't required the use of any complex methods for the electrolysis itself, and we haven't required an inert atmosphere to do either of them. With this video, we're going to be stepping up the difficulty ever so slightly. We're going to be isolating lithium from molten lithium chloride. I should note that this lithium chloride is not the product of the lithium extraction we tried to do a couple of videos ago, because that was a bit of a disaster. That was the plan, but I ended up just buying lithium chloride online to do this project. The process for producing lithium metal is very similar to the processes we've done for aluminium and sodium. All we need to do is melt lithium chloride, apply electrolysis to it, pass some DC current with a couple of electrodes, and lithium is made like that. It's the same way they do it in industry. It doesn't have a special name, but that is what's done. Now, when we do actually perform the electrolysis of molten lithium chloride, of course, reduction occurs on the negative electrode, that's the cathode. So electrons are given to the lithium ions in the melt to form lithium metal. And on the anode, the positive electrode, oxidation occurs, so electrons are taken away from chloride ions to form chlorine gas. For our electrodes, specifically the anode, first off, we only really have one choice for the material that we can use to generate chlorine, and that's graphite. It's the only material cheap enough to handle the generation of chlorine at these kinds of temperatures without contaminating the melt or breaking apart really quickly. So we will be using graphite for our experiment today. It should work. Sadly, we can't use graphite as our cathode for generating the actual lithium metal, because as I found out in the sodium video I did a few months ago, carbon actually reacts with alkali metals at high temperatures. I didn't know this, but this is apparently a well-known fact, so we won't be using graphite as our cathode. Instead, we have a few other options. The first one we're going to be going with today is nickel. I have some nickel on an electrode here that we're going to be trying out first. Nickel is just a pretty good all-round, very conductive electrode that is resistant to corrosion and generally works well as a cathode for molten salt electrolysis. However, in the experience of other people who have done this process before as an experiment, I've talked to a lot of people who have done this exact experiment, extracting lithium metal by electrolysis. Everyone seems to say that iron or steel as a cathode, which I also have, is much better, simply because the lithium that forms on the electrode beads up nicely as a result of using iron as an electrode. I'm not quite sure why this is. I'm thinking maybe the interfacial tension between lithium and iron is ideal for forming nice beads, or maybe the iron forms a low concentration alloy with the lithium that has more favorable properties for forming beads. I really don't know, but everyone else says that it's a really excellent choice for collecting the lithium after we've finished with our cell. So we will be trying that if the nickel doesn't work. Now, I said before that the generation of lithium by this method is a little bit more difficult than the sodium and aluminium that we've done before. In particular, the reason for that is the danger. We're not just melting molten salts here at temperatures of above 300 degrees. We are generating chlorine gas at high temperatures and in large quantities. I've dealt with chlorine gas before, not in the amounts that we're going to be dealing with it today, and certainly not in an environment where we can't capture it and lead it into a gas scrubber or something like that. In this case, we really can't capture the gas and manage it really well. It's just going to be vented to the atmosphere. Even though we are in a well ventilated area and a very long way from people who might be at risk of breathing in the chlorine we generate, it is absolutely essential that we wear a mask. So I have here a mask that is rated for chlorine gas. I will be wearing it the vast majority of the time we do this experiment because that is a very, very necessary thing to do with the quantities of chlorine that we're generating today. The second thing that makes the production of lithium metal a bit tricky is the melting point of our lithium chloride. Generally, the melting point of lithium chloride is 605 degrees Celsius, which, when you think about the fact that we're generating lithium metal and chlorine gas really close together, it seems like the recipe for a bit of a disaster, either a lithium fire or explosion, possibly. Luckily, industry has the answer for mitigating the risk of lithium catching fire in the process by lowering the melting point of the lithium chloride, and we can do that by using a eutectic mixture of two salts, that being lithium chloride and potassium chloride. So if we mix these two together such that the potassium chloride is at a concentration of 42% by molar ratio, we can lower the melting point of the lithium chloride to around 352 degrees Celsius. And even better, when we electrolyse that mixture, we still get lithium metal because at those temperatures, it's easier to reduce lithium ions than it is to reduce potassium ions. As I said, that's what they do in industry to make lithium metal, and we've got no reason to do it any other way. To actually melt down our eutectic mixture, I'm going to be using a stainless steel measuring cup as the crucible. It's not the best choice, it's not the best idea to melt down chloride salts in stainless steel, but it's what I've got and it should last long enough to do a couple of experiments for generating lithium metal. So that's what I'm going to do. And with that, I think that's everything, so let's get started. Okie dokie, so starting our experiment now, what I've got is our eutectic mixture in a stainless steel measuring cup, slowly heating on the furnace. We have set up already and connected to the power supply a graphite anode to generate chlorine and a nickel cathode to generate our lithium. Of course, we're trying nickel first because we expect it to hopefully give us a slightly purer product, but if things don't go quite as planned, we will be trying out an iron electrode. Anyway, we've just got to wait for our mixture to melt and then we'll turn on the current and see what happens. Right, looks like we're just up to temperature now, so I'm going to turn on the current. We've set things to 5 volts and we'll see what happens. Ready, go. That is 5 amps there. Oh, something's going on. Popping. It's exciting. Better stand back. Okay, I'm going to turn that off for a bit. I don't like how that's popping. I'm going to wait for the top layer. I think we've got a solid layer of salt on the top of our cell, and we're just going to wait for all of that to melt properly and then restart our electrolysis. After heating up a bit more, a second attempt. We've got a few amps flowing. You can see some chlorine coming off the cell, off the anode in particular. Alright, I think I'm going to call it for this one. We've had it running for about 10 minutes. We're seeing a lot of chlorine on the anode, but on the cathode we're not generating much in the way of lithium. I do see a couple of tiny specks every now and again of very shiny, what I assume to be molten lithium from our melt, but they disappear very quickly, and I think we just don't have the right setup to generate lithium like this. I think we might require an inert atmosphere or something like that, maybe argon or something. So I'm going to turn this off, and then I'm going to maybe replace our nickel cathode with iron, because other people have tried that and we know that that works. So with everything back to as it was before, we can turn back on the current again at 5 volts. And we get some popping initially. And I'm hoping that now, at this point, we've got about 2 amps flowing through the cell. I'm hoping that we get some lithium on the cathode now. I think you can see on camera there, I'm actually seeing something shiny forming on the cathode. Just a small blob of metal. I'm pretty sure it's not just part of the iron on the electrode. I'm pretty sure it's a glob on the side. So hopefully in a few minutes we might have a sizable chunk of lithium forming on the cathode. I'm not sure how well you can see that now, but just 5 minutes in, we've got quite a sizable chunk of lithium, I think. Righty, so with that lithium that we just scooped out of the cell in this little scooper here, there's one good way to check whether it is actually lithium, and that is of course to react it with water to see if it burns. So I'm going to do that now. Well, didn't catch fire, but that is definitely a reaction between lithium and water there, so that's excellent. Alright, look, we've had it running for over an hour now, I think, and at this point it doesn't look like the cell wants to generate any more lithium, and I say it's probably done enough for us, so I'm happy to shut this down. I'll show you the amount of lithium that we have just made. If you can see in there, that is all of our lithium stored in mineral oil. I'm going to do my best to try to melt it all into one glob, and then I'll get back to you once I've tried doing that. But as I said, for now I'm going to shut down the cell and start packing up. Alrighty, look, trying to melt down our lithium again into one big chunk was a bad idea. Alright, we had quite a bit of lithium to start off with, and in trying to melt it down, we're left with, alright, I've put it into a vial, this much. And it is definitely lithium. It floats on mineral oil, which is a pretty telltale sign of it being lithium. It's also pretty shiny. It's a bit dirty, as you can see, and I wasn't actually able to melt it all into one chunk. I could melt it into one solid piece, but then I couldn't pour it out of the spoon that I was using to melt it all down in. So it was a bit of a disaster. I'm pretty sure I lost about half of the lithium that we extracted, which is very disappointing. So as a result, I'm actually going to try again. You can see I'm now melting down another lot of our eutectic mixture, and then we're going to electrolyse that to try to get some more lithium. Additionally, I forgot to use this power supply. I've had this current controlled, voltage controlled power supply for ages, and I always forget to use it. I always go for the stupid PC power supply out of an old computer that can only do 5 volts or 12 volts. I mean, there's a lot of amps that you can get out of that, up to 20, which is quite nice when we're making aluminium or something. But for a project like this that only needs, well, I want to run 6 to 8 amps through the cell, this power supply is perfect. It can supply up to 30 volts and 10 amps. So I think we will be able to make more lithium this time round. And maybe we'll have enough lithium to be proud of. Right, let's turn on the current. Oh, yes, excellent, excellent. I'm going to go grab my mask, and then we're going to try setting this to 6 amps, I think. See if we can make lithium a bit faster this time. That's 6 amps there. And we can see we're already generating a little bit of lithium. It's a bit hard to see on camera, but it is there. Alright, I'm calling it. It's been an hour. I think that is a pretty reasonable yield. So, yes, I'm pretty happy to call it quits now, and we will get this into the same vial as the other stuff and see how much we've got all up. Now that we've actually finished the reaction and I've packed up the cell, we can have a look at the 3 electrodes we ended up using for the process. First of all is the nickel cathode that we started with. Interestingly, it did actually work in generating lithium, I found out, because after taking the nickel out of the cell and putting it in some water, there was a very clear generation of hydrogen bubbles. So we did have lithium actually stuck onto the surface of the nickel there, but we just weren't able to get it to bead together. Exactly what we expected to happen, pretty much. Maybe if we had have run the cell for a bit longer with the nickel cathode, we would have actually seen enough lithium to extract, but maybe the surface area was a little bit too high. Additionally, you can see quite a bit of corrosion around the upper parts of the electrode, obviously due to the chlorine that was generated and the high temperatures. So nickel isn't really the ideal electrode for this kind of process. Iron, however, or steel, seems to have done perfectly well. I mean, you can see there's no real attack on the electrode, save for a little bit of oxidation on the wire above where it was in the melt. The actual end of the electrode is looking perfectly fine. It hasn't been touched. The real winner here actually was the graphite electrode that we used to generate the chlorine gas, because if we actually have a look here, you can see that there's pretty much no erosion at all on the electrode, despite the fact that it was generating chlorine gas at a temperature of 350 degrees for over an hour at a current of over 6 amps. It pretty much looks as good as new. So I'm very impressed with that, and that's really good news for the future molten salt electrolysis projects that we're going to do. Graphite works a lot better than I thought to generate chlorine. We can also see that the stainless steel crucible, the measuring cup that we were using to actually do our electrolysis in, has done remarkably well. All right, if we actually have a look at that, you'll notice there's a fair bit of oxidation, but really that's just a surface coating. And if we really wanted to, we could probably clean that off and the measuring cup would be as good as new. You can see in there's still a little bit of that lithium chloride, potassium chloride eutectic. I've left this soaking in water for about a day and it's nearly finished dissolving it all out, but there's a little bit to go. And last but certainly not least, we do actually have the total lithium yield we were able to obtain from the process. You can see there, that's quite a sizable amount, I'd say. And of course, we weren't actually able to melt it all into one droplet, so that was a little bit disappointing. Also, you can see we have a few shiny bits, maybe down the bottom there, that one, bit around the edge there, but a lot of them have turned black. That is, of course, due to the nitride coating on the lithium surface that forms in contact with air, because lithium reacts with both oxygen and nitrogen from the air, and the fact that it floats on mineral oil means it's really difficult to stop that from happening. Maybe I could push it down to the bottom with a bit of fiberglass or something to prevent it from just sitting on the surface, but I'm probably not going to bother doing that. Also, our total yield of lithium isn't all that great. I mean, at least in terms of mass, because the density of lithium is so low. It's a very not dense element. Is there a word for not dense? I'm not really sure. We have maybe half of a milliliter to 1 milliliter worth of actual lithium metal, which corresponds with less than half a gram. I'm not going to get it out and weigh it, simply because the surface area is really high and weighing it would inevitably oxidize it really quickly, and I really don't actually want to do that. I want to keep it in this vial. So yes, I'm not going to weigh it, but our yield is probably less than half a gram, which sounds bad, but it's really not too bad because the molar mass of lithium is actually extremely low. It's only about 6.9, I think, grams per mole. So that's actually quite a sizable amount of lithium that we have here. The final thing that I wanted to show you at the very end of the video is if I get out one little bead of lithium, if I can grab it. That looks like a good one. One of the cool properties of lithium actually is the fact that it's quite a soft metal. It's not quite as soft as sodium as we looked at before, but it is soft enough to cut with a sharp enough knife and enough force. And if I show you here, if I squeeze this really hard with this pair of tweezers, you can see it just kind of deforms and bends as a result of it being such a soft metal. Rather cool, I think. And to finish off the video, the very last thing we'll do, the reaction that everyone always wants to see when we're talking about the alkali metals, the reaction of lithium with just regular water. So I have some water in this beaker. I have that little bit of lithium that we were just demonstrating before. So if I just put this into our beaker full of water, we should see it's a somewhat vigorous reaction. Doesn't quite catch fire. It's not quite reactive enough to do that in quantities as small as this, but if we had larger amounts of lithium, of course, we would see flames and possibly even an explosion. So while you might want to see that, I definitely think it's a good thing that we're not doing these things on such a large scale. So there we are. That's the lithium we were able to make today. I'm quite proud of that. I think that's a reasonable amount. And of course, here's the sodium we made in a previous video, and the aluminium we made. So we're getting quite the collection now of metals that we can extract by molten salt electrolysis. With our next molten salt electrolysis project, we'll be stepping up the difficulty even further. We'll be trying some reactions that haven't been successfully done on YouTube to this date, so I'm a bit worried about that. But for now, we can just enjoy our success for making lithium metal, and until our next video on the topic, I'll see you later.